Okay, I guess let's get started. This is the last lecture of this course. I guess we're going to continue with the spectral approach for clustering. So I pre-read some of the reviews of the last lectures. I guess so. Last lecture, I think we did the stochastic block model, and one of the main findings is that if you do eigendecomposition, so our goal was to do eigendecomposition on the graph G from the stochastic block model. And we have shown that if you do eigendecomposition on the average graph G, the expectation of G, then it does give the hidden community S and S bar, right? I think last time we showed that the second eigenvector is something called U, which will look like 1, 1, 1, and minus 1, minus 1. And this is S, and this is S bar. So basically, if you just take the second eigenvector of the expected graph G, then you get the hidden community. So, and we have argued that it suffices to show that the graph G and the expectation graph, expectation G, are close enough in the operator norm. And this is because if you consider this equation, right, so you subtract the first eigenvalue from G, and then what you get is that G minus the first eigencomponent is equal to this perturbation matrix plus the contribution of the second eigenvector. And if you take the eigendecomposition of this matrix, which is something you can compute easily, then if you take the top eigenvector of the left-hand side of this equation, then you are expected to find something close to U. And as long as G minus expectation G is something small. And how small it is, I didn't really formally do this, but essentially you need this perturbation to be much smaller than the signal, right? So you need a perturbation in operator norm much smaller than the rank 1 signal in operator norm. And you can compute the operator norm for the rank 1 signal very easily, which is something like P minus Q over 2 times N. So basically, we are trying to show that the concentration, right? This is a concentration inequality because you are trying to prove that G concentrates around expectation of G in this spectral norm sets. I'd like to show this proof. This is a little technical proof, but the proof is not very long. And also it kind of relates back to what we discussed in lecture 3 or 4, where I guess probably you remember that I said that this concentration inequality is probably one of the most important thing for this class because this is this kind of one of the, if you pick one technical tools in statistical machine learning, I think it's probably concentration inequality, in my own opinion. So it's probably useful to just review why the concentration inequality can help us to do something like this. So I'll give a proof for this. So the proof looks like, so we're going to prove that so our lemma is that with high probability, G minus expectation G in operator norm is less than square root n log n up to a constant factor. So, and at the first sight, this is not exactly the type of concentration inequality we have talked about before, because before we're talking about scalars, right? So we're saying that if you have expectation of if some random variables have some empirical samples and the empirical average concentrates around the population average. So here it's a little bit different because G is a matrix and the expectation of G is also a matrix. You are doing some kind of like matrix concentration to some extent. And your measure of the similarity is not just the absolute value in the difference of the absolute value of the difference, but it's about something like the operator norm of the matrices, right? Of the differences of the matrices. So however, you can actually turn this into something that we are familiar with very easily. So what you do is the following. So you say that this is still uniform convergence, as you see. That's the main idea. And why this is the case? This is because you can easily interpret the operator norm as follows. So G minus expectation G operator norm, this is equals to the max over some v. Let me write it down and explain. So minus this is just because the operator norm, for symmetric matrix, I think the definition is, if you have a symmetric matrix A, and then the operator norm, I guess there's absolute value here. So the operator norm of matrix A is exactly equals to the maximum quadratic form that you can achieve by hitting it with a non-one vector. So, and once you do this, you see that this becomes a scalar now, because this quantity is a scalar. And you can decompose this into max v2 norm square, and then you get v transpose gv minus v transpose expectation gv. And this is a sum. So what is this? Maybe let me write down more explicitly. This is max. This is sum of vi, vj, gij, ij, both I and j are in n, minus the expectation of this random variable. And now this becomes a sum of independent random variables, and this becomes the expectation of this sum of independent random variables. So now you can use concentration. If you don't have the max, you can use concentration for it. But this is what exactly Hoff inequality is for. And how do you deal with the max, right? So then the max, this will be the part about uniform convergence, right? Recall that the whole point of this uniform convergence is that if you fix the parameter, suppose you think of v as the parameter. So the point of uniform convergence is that if you fix the parameter, you can use Hoff inequality to prove the concentration, to prove that empirical is not very far away from population. And the challenge of uniform convergence is about how do you take the max, and here you still have a max. So I guess there are multiple ways to deal with this concentration. Of course, the easiest way is probably just invoke some existing theorem. There are this kind of theorems in the literature as well. But if you want to do it yourself, I guess there are two ways. So one way is that you can use the Rademacher complexity machinery. The Rademacher complexity machinery, I guess it's a while back. Like we discussed this like probably 5 weeks ago, and I think one of the techniques is that you do symmetrization, right? So far this is not a symmetric form, and you introduce some Rademacher variable and you symmetrize it, and then you can proceed with all the random. You can essentially view this as a Rademacher complexity of some function class. So you can go with that. I think that's actually a pretty clean and nice way. I'm going to leave this. If you're interested, you can do it yourself. I believe it's not very difficult. What I'm going to show here is that I'm going to show us an even more brute force method, which use actually the first technique we introduced in your class, the brute force discretization. Recall that before we talked about Rademacher complexity, we said that in many cases, actually you can just deal with the continuous function class, the uniform convergence for continuous function class with a very simple discretization. So and what we do is that, so what we do here is going to be just that you for fixed v with 2 norm equal to 1, we can use Hoff inequality. Use Hoff inequality. So what you get is that with probability at most exponential minus epsilon square over 2, I guess I'm not expecting you to check it, on the fly, but you can just basically plug in the Hopf inequality without any modification. You get Vi, Vj, Gij is close to its expectation. Okay, so the probability that it deviates from expectation is at most exponential minus epsilon squared over 2. And then you take epsilon to be something like big O of square root n log n, so that your failure probability, that this means that exponential minus epsilon squared over n, this is something like exponential minus big O of n log n. This is a pretty small failure probability. And then you take a discretization, of the unit ball of with granularity something like some 1 over poly n. Right, this is what we did. It's a long time ago, I know, but I think this is what we did at lecture 3. I think you take a very precise, you use a very small granularity, but it doesn't really matter because at the end of the day, the dependency on the granularity is only logarithmic. So your size, the size of this cover is exponential n log n. And then you can take a unit bound. Over this discretize. So, and then because your granularity is very small, right, it's only inverse Pauli, so you only lose inverse Pauli, and inverse Pauli is smaller than any of these quantities. So then basically, eventually you get that you take a unit bound, we get with high probability, you have this. Is less than epsilon, which is chosen to be square root n log n. So I guess I'm skipping a lot of details because I think today we don't have a lot of time to complete all the materials. So I'm making it a brief, but I think you kind of get the rough point. And if you work out, it wouldn't take too much time to work out details. And I kind of like this method too. If I were to say my preferences between these methods, sometimes I like the method too because you can do this very quickly yourself, and you know exactly what the dependencies, where the dependencies come from. And if you do the rather more complex, it will be much cleaner. You will get better constants, you get cleaner proofs. But sometimes it's a little bit less transparent because you have to go through this whole machinery. And why this is useful, right? This is useful because now we get this lemma, right? So the lemma is that the G and expectation G is only different on the order of square root n, and you can compare that with the signal. So now, compare the noise level, which is of n square root log n, versus the signal level, which is p over q times n, and p minus q over 2 times n. So then this means that if p minus q is much bigger than 1 over square root n, then can recover the signal, the vector u, approximately. So we can see that you only need p and q to have some separation, but not a lot of separation. And the separation depends on the size of the graph, which also makes some sense because the more no vertices you see, the clearer the structure is in some sense. You have more kind of, like suppose you just see 2 users, right? Everything's kind of too random for you to tell which one is from which community. But if you see a million users, you can use a lot of different users to cross-validate in some sense yourself and to detect the 2 communities. All right, so I guess this concludes the stochastic block model part. I guess there are some other small remarks which are not super important. So you can also actually can recover the exact community by some post-processing. So here, what I showed is that you only can recover the vector u approximately, but actually you can post-processing to get the exact community under certain conditions. I think under the conditions that I'm giving here, you can do it. And actually, because this is a very precise mathematical structure here, so there are a lot of works that in the literature on this, and you can actually get even the exact constant here. So here I'm writing p minus q is larger than 1 over square root. So it's definitely very, very loose. You can get the precise dependencies that you need to recover, and then you can have the precise threshold. Below that threshold, you cannot recover anything. Above that threshold, you can recover something, and above another threshold, you can recover exactly. So all of these are in the literature if you're interested. And you can extend this to multiple blocks, so and so forth. Okay, so this concludes with the stochastic block model, and now I'm going to move on to another kind of very, in my opinion, pretty important literature, which is about clustering the worst case graph. And still, the theme is that if you do eigendecomposition, you are going to recover some approximate structures in the graph. So we are still going to use eigendecomposition, but the analysis will be different because here we don't have the stochasticity from the graph. So and because you have a worst case graph, you have to also somehow define what do you mean by the hidden community, right? So because before in the stochastic graph, you start with community, you generate a graph, and now you are just given the graph. The graph is just some edges. You have to say what you're trying to recover. So let's start with that. What's our goal? So this requires us some definitions. So let's say given a graph G, as the vertices is called E and edges is called vertices is called V and edges is called V. So let's define this so-called conductance. This is actually a pretty important notion which shows up in many different areas of math. So of course it's a different form. So here is about edges, about graph and edges. In other cases, you can define conductance in high dimensional space as well, which are essentially the same definition, but it could look a little bit different. So the conductance for a graph, so you suppose you have a cut. That's called S and S bar, right? You cut the graph into two parts, S and S bar. And the conductance of S is defined to be the following. So you have the number of edges between S and S bar over the volume of S. Let's define both of these more clearly. So E S S bar, this is the total number of edges from S to S bar. But this is an undirected graph. There is no, maybe I should call it between S and S bar, just to be precise. So, and which, mathematically, this is really the sum of I over I in S, J in S bar, Gij. If I use Gij as the adjacency matrix, I'm overusing the notation a little bit. G both denotes the graph and also the adjacency matrix of the graph. And the volume of S, this is the total number of edges. Total number of edges connecting to S. So which means that you look at how many edges satisfies that one endpoint is in S. So I needs to be S and J can be anything, and you have Gij. So if you draw a graph, something like this, suppose you draw a graph, this, maybe this and this, and you define this cut. Suppose this is S, then what is ES S bar? So ES S bar will be counting these two right edges because this is from S to S bar. And the volume of S will be counting all the edges connected to S. So which means basically all the edges drawn here, all the green edges are counted. So, and you can see that by the definition, it's true that the volume of S is always. Okay, so what this definition is for? This is trying to characterize how, I guess, as the word conductance indicates, it's trying to characterize how good the cut is in some sense, like how separated S and S bar are. The smaller it is, the more separated S and S bar is. But you do have to normalize by the volume, right? So in some sense, in the number of edges, it's already between S and S bar, it's already capturing how separated an S and S bar are. But you want to normalize with the volume to make it more meaningful. I guess that's what I'm going to argue in the next. So I guess before that, let me just get some basic information. So the volume of S is bigger than the number of edges between S and S bar. That's trivial. So this means that the conductance is always less than 1, and you are trying to make the conductance as small as possible. And another thing is that the volume of S plus the volume of S bar is equals to the volume of V. This is the total number of edges, right? So and that means that so this means that if the volume of S is less than the volume of V over 2, then the volume of S is also less than the volume of S bar. And this means that the conductance of S is bigger than the conductance of S bar. So there's some, so you should have a definition that somehow doesn't depend on how do you name S and S bar. S and S bar are symmetric, but here the conductance of S and S bar are different, right? So that's why to kind of like remove this symmetry, confusion between the symmetry, you just insist that you are always talking about. So we will insist that we always only talk about S such that the conductance of S, the volume of S is less than the volume of V over 2. So you're only taking a smaller part of S and use that to define the conductance of the cut.
Why don't we just define conductance so that it normalizes by the volume of V?
Yes. So if you normalize by the volume of V, first of all, the problem is that it means that you didn't normalize because V is a constant. You have to normalize against something. I guess I'm going to tell you why you have to normalize, but if you want to normalize, you have to normalize with something that changes as S changed. Right. So here I'm only trying to deal with the symmetry for so far. It's like you only look at the conductance on the smaller side. This is not really that much because you don't want to cheat by saying that I have a very, very large side and I only have like one point in S bar, and it sounds like my conductance is very small, but actually you should measure the other side. Yeah. Okay. So, but now let's okay. So maybe before proceeding answer the question why we have to normalize, so we can also define the phi of G. This is the conductance of this is the sparsest cut. This is the so-called sparsest cut of G. Our sparsest cut value of G is defined to be the minimum possible conductance. But again, you require that S is the smaller side of the two cuts. So you minimize over the conductance of S. You minimize the conductance of S with the constraint that the volume of S is less than the volume of V. So, basically you just want to find a cut that has smallest conductance. And okay, now let's talk about normalization. So why we have to normalize? I think the reason is pretty much just because if you don't normalize, then if you just minimize, right? If you just look at E as S bar, is somewhat minimized, is typically minimized when S is small. So suppose you draw a graph, for example, I guess. So if you don't normalize, basically you prefer to pick a set S that is itself is very small, so that it doesn't connect to the other part. So for example, let's see. Suppose you have a graph like this. Okay, I guess I'm okay. What I'm doing here is I have a. Suppose you have a completely connected subgraph, right? So you have n over 2 nodes, n over 2 nodes, and within each of the subgraph you have complete connection with each other, and then you have some connections, some very small number of connections between them. Maybe every node is connected to 2 of them, something like this. Okay, so it sounds pretty clear that you should just really the best cut you should get is this one, right? Because within the cluster you have full connection, and across the 2 clusters you have some number of, let's say, 2 edges per node. So it sounds pretty clear we should do this. But if you use the metric E as bar, then you see that some other cuts will have smaller number of edges across the thing, because you can just take this to be S1, because the S1 just contains 1 node. So then E of S1, S1 bar is basically how many edges comes from S1 to S1 bar, basically the number of edges connected to S1. This is n over 2. But the good cut, let's say the good cut is S2. So S2 bar is definitely something bigger than n over 2, because you have n over 2 probably times the number of green edges, the number of blue edges per node, something like 2 here. I'm drawing basically two edges per node, something like this, right? So basically, even it sounds like you should get S2, but if you use the unnormalized version, then you would get S1. So, however, if you normalize, then it's a different game, right? So if you normalize, if you look at the conductance of S1, then this is E of S1 bar over the volume of S1. This is n over 2 times over n over 2. I think the volume of S1 is n over 2. So this is 1. So if you look at phi of S2, then this is n over 2 times 2, something like this, and then you have the total number of edges connected to S2. That's actually a big number. That's probably something like n over 2 times n over 2 minus 1. This is the number of edges within the S2, and there are some edges between S2 and S2 bar, something like this. And this would be something like roughly, I think, 2 over n. So the conductance of S2 is much smaller than the conductance of S1, if you normalize. Questions so far? Okay, cool. So now we have to kind of define the goal, right? Because you have a worst case graph, your goal is to, so we have said that the goal is to find approximate sparseness cut S hat, meaning that you want S hat to satisfy that the phi of S hat is close to the sparsest possible cut phi of G. And the approach we're going to describe is still eigen decomposition. So how do we do this? Okay, I need a, okay, there's for us to even state what we mean exactly by eigenoptimization and what kind of like results we can have. So first of all, let's di to be the volume of the node I, right? You take a single node, you take the volume, this is di. And this is really just the degree of node I, right? So the volume of the node is really the degree of the node. And let's take D to be the diagonal matrix that contains Di's S entry. And let's define this so-called normalized adjacency matrix. It's called A bar, which is D minus a half G times D minus a half. So where G is the adjacency matrix. Recall this is our notation with a little bit of abuse of notation. So what is this matrix? What does this really mean? This really just means that I guess you have 1 over square root di, d1 up to 1 over square root d, n times g times 1 over square root d, 1 up to 1 over square root d. And a diagonal matrix multiplied on the left means that you scale all of the rows. And the diagonal matrix on the right-hand side, as a right-hand side multiplication means you scale all the columns. So basically you scale the columns and rows simultaneously with these numbers. If you do the exact calculation, what it really means is that the Aij, the ij's entry of the normalized adjacency matrix is really just the adjacency matrix over square root di times square root dj. So this sounds a little bit complicated, but in most of the cases, I'm only stating this mostly for formality because in sometimes the key thing it can be seen by assuming the graph is regular. So in most cases, suffices to think of G as a regular graph. A regular graph means that all the degrees are the same. So let's say, suppose I say G is a kappa regular graph, meaning di is equals to kappa for every I, then its adjacency matrix is really just 1 over kappa. Normalized adjacency matrix is just 1 over kappa times Gij. So in some sense, you really didn't do much except just changing the scaling of this. But this scaling is kind of like important in the formula sense because it's going to make the formula very clean, but it's not fundamentally super important. So this is pretty much if you don't want to think about the di and dj's, you pretty much can think of this simple case where you have a regular graph. Okay, so and once you define the normalized adjacency matrix, you can also define the so-called Laplacian matrix, which is I minus the normalized adjacency matrix. I think you probably see that one of the reasons why we have to normalize is that if you don't normalize, it doesn't make sense to take the differences between it and identity. Identity is something that doesn't have a scale. So you have to normalize it so that you can kind of take the diff with identity. And this Laplacian matrix is really not doing that much. It's not that different from normalized adjacency matrix anyway, because they are pretty much like everything corresponds to each other, right? So like the eigenvector of L is the same as the eigenvector of A bar, and the spectrums are just a flip with each other. So let's say suppose L has eigenvector value lambda 1 up to lambda n. Let's say, suppose, I think in this literature, you always want to kind of like order them, and then with the eigenvector, say u1 up to un, then this means that this is equivalent to a bar as eigenvalue 1 minus lambda 1 up to 1 minus lambda n. Now I'm sorting in this decreasing order, and with eigenvector the same eigenvectors. Right. So, but as you see, like so far, so you don't even have to think about the Laplacian, right? The Laplacian will come into play at some but later places. But so far, you can just think of like Laplacian is a flip version of normalized adjacency matrix. Nothing really different. So, okay, so these are a little bit abstract preparation. And now let's see what we can do with this. So this is one of the, in my opinion, pretty important theorem. It's called Cheeger's inequality. Actually, this dates back to 1969 by Jack Cheeger. So it says the following. It says that lambda 2, this is the second eigenvalue, over 2 is less than the conductance of G, which is less than square root 2 lambda 2. So it connects, so why this is a very important thing, it connects the conductance, the cuts, the sparses cut, to something linear algebraic, to the eigenvectors, right? So the sparses cut is a very combinatorial stuff where you have to, if you really want to find sparses cut, you probably want to enumerate all the possible cuts and to find sparses cut. At least the definition requires, it's a combinatorial thing. But this inequality is saying that somehow the sparses cut value has a lot to do with the eigenvalues of the Laplacian or the adjacency matrix. And in particular, it's very close to the second eigenvalue of the Laplacian matrix. And moreover, you can also find find the approximate cut as hat, such that this cut as hat, the conductance is less than square root 2 lambda 2, which is less than 2 times square root phi of G, computationally efficiently. And not only computationally efficiently, but also actually pretty explicitly, what you can do is the following. By rounding the eigenvectors. I guess rounding really means the following. This is the rounding in the approximation algorithm sense. I guess, if you don't know where the terms come from, doesn't matter. So here is the procedure to find such a set S hat. So suppose you take U2, suppose the U2 is equals to, the coordinates are beta 1 up to beta n. Is the second eigenvector, is the second eigenvector. And so you can take a threshold, which is chosen to be beta I, and consider the set S hat I to be all the coordinates that satisfies that beta j is less than tau. So take a threshold, but you don't have to consider all the possible thresholds. It's not necessary because, as you see, so you take a threshold tau, and the threshold is chosen from one of these coordinates, and you say you look at all the coordinates that are smaller than this threshold, and that's your set as hat I. And then one of this, so you have basically n of these sets, right? S1 hat, S2 hat, S3 hat, so on and so forth. So one of this S hat i's satisfy phi of S and height is less than 2 times square root phi. So one of these side will be a good cut. So I guess I'm sticking this in a formal way so that it seems to be a little confusing. So what you really are doing is the following. So you sort. So I guess in plain language or in more clear, in formal language, you first sort the coordinates. Suppose you sort the coordinates first, and you get beta 1 less than beta 2, so and so less than beta n. And then it's saying that if you take this will be s hat I. Right? This will be the first I coordinate, and that would, and one of this cut will be a good cut. So you can try one cut which is like this. You can try another cut which is beta 1, beta 2. And you can try another cut which is beta 1, beta 2 up to beta I. And one of these cuts will be a good cut on the graph with small conductance. And of course, you have to you have to remap the coordinates back to the original coordinate system because you have sorted the coordinates. But this is the main idea. Any questions? So like I guess another way to think about this is that if in a stochastic block model case, the second eigenvector was something like this, right? And pretty much in that case, if you take a threshold here, the smaller values correspond to one cut and the larger values correspond to another cut. But here you don't know where the exact threshold should be. You should try all the thresholds, beta 1 up to beta n, all of them. Okay, cool. So this is a pretty magical theorem in my opinion. I'm not going to prove it. I think there are, if you are interested, I think there are a lot of lecture notes that can prove this. I guess what I'm going to do is that I'm going to. Go ahead.
Is the theorem that exactly one of these S hat I's satisfies that, or at least one?
At least one of them. Yeah, and if you are able to, and you can enumerate all of them, just try all of them and see which one satisfies it, and they are done. So the proof is pretty non-trivial. It's not very long, but it's kind of non-trivial. So I'm going to skip the proof. I'm going to link. I see some questions here. So the question online here is that the hat Sj found this way isn't the best possible cut, right? Yes, so you are not guaranteed to find the best possible cut. You're only guaranteed to find a cut such that the cut value phi of S hat I satisfies that it's less than 2 times square root phi of g. If you get phi of g here, suppose you magically change this to phi of g, then that means you get the best cut because phi of g is the value of the best cut. Of course, maybe there are multiple best cuts as well, but you definitely find one of the best cuts. But however, we don't have that strong of a theorem. We only show that it's 2 times square root phi of g because so you lose something, right? Square root phi of g is bigger than phi of g, by the way, because phi of g is less than 1. So you lose some factor in terms of like the best possible the conductance. I hope that answers the question. And in some sense, you have to lose a little bit to some extent because I guess this is in some sense post-mortem but if you think about it, in retrospect, one of these quantities is very combinatorial, the sparseness cut, and the other point is very linear algebraic. Sounds unlikely that they can be exactly the same, right? So it's already kind of fortunate that they are somewhat related, in my opinion. And I want to kind of mostly discuss some of the intuitions or the more basic quantities, like some of the intuitions why this can be possibly true, but I want to give the full proof.
The statement of the theorem said that we can find S hat such that it's less than square root 2 lambda 2,
yeah.
Which then is less than is that what we're actually finding? And we're just saying that, oh, by this, transitive property of equality, whatever, then that's less than 2 square root of 2g. And in that case, like, I think we just care about the relationship to g, right?
You just care about
the comparison of r cut to the cut of g, as opposed, like, it's not significant that it's like the square root of 2 lambda 2 isn't significant, other than that it lets us show this inequality.
Sure. Okay. So, yes. So first of all, yes, you are right. So how do you get this inequality? This is just by using this part. Right. So that's true. And second, yes, probably the first order bit you care about is comparing with phi of g, and this is just some intermediate things. Yeah. However, yeah, that's the first order bit. But I think if you look at the proof, you do have to, like, somehow the eigenvalue, the eigenvalues have to show up somewhere. So
do you like lose any, like, do you not lose any significant amount in that second half of the inequality? So like maybe your cut is actually pretty good, because square root 2 lambda 2 is actually relatively small, but then you lose more in that second inequality.
I think it's possible, but we don't really know. Like, it's kind of like very hard to. I think there are hard instances in both cases. Like this thing can be both close to 2/2, or it could be very close to this side. Yeah. Cool. So I guess I'll focus on some intuitions and why. Like, the first thing I'm going to discuss is that I think this is again about the scaling and to some extent. So first of all, the smallest eigenvector. Why you take the second eigenvector? I think that's always something that seems to be magical to me at first sight, and then after I spent some time, when I first started this, I realized the top eigenvector, like as I kind of like say last time, the top eigenvector is kind of like a background. So either the smallest eigenvector of L or the top eigenvector of A bar, this is kind of like not that interesting. And why it's not interesting is pretty much only trying to get only capturing in some sense, I call it background, it's kind of like a background density. So what I really mean by this is that of the graph. What I really mean by this is that, let's say, suppose when G is kappa regular, then we know that, I think we actually have stated this in the previous lecture. So O1 vector is top eigenvector of A of G of the adjacency matrix, and thus also top eigenvector of A bar, which is just 1 kappa times G. Right. So when G is regular, then the top eigenvector is really just it's just a all-one vector. And when in more general case, it's really just involves the scaling based on density. So for more general G, what happens is that the top eigenvector is really just this one. It's square root d1 up to square root dn. The scaling doesn't matter here because the eigenvectors, any multiplication of this is also an eigenvector, so I didn't care about the scaling. So this is the top eigenvector of A bar, so smallest, which means the smallest eigenvector of Laplacian. Right? Why this is the case? You can verify this relatively easily. So A bar times U1, this is a matrix notation, and you look at the J's coordinate, I's coordinate. This is equals to the sum of J over J, sum of Aij bar times Uj. And Aij bar is a scaled version of the graph. So Gij over square root di square root dj, and uj is square root dj, and this is a sum over j. So you first cancel out this two, and you get 1 over square root di in front, you get this. And recall that this is actually precise definition of the degree. This is the total number of edges connected to the graph, so get 1 over square root di times di, which is square root di. So that verifies that u1 is an eigenvector. This means a bar u1 is equal to u1. So basically, as before, the top eigenvector is not doing much. It's really just capturing the density, the degrees of the graph. And the second eigenvector starts to talk about the interconnections. It has more about the relationship between edges and kind of hidden communities. And now let's look at some intuitions about why this why the Laplacian, like why somehow this eigenvector is related to the cut. So here is another way to think about it. So if you look at the contractive form of the Laplacian, so what is this? This is the V transpose I times V minus V transpose A bar times V. Let's just brute force rewrite this. This is sum of Vi square, I from 1 to n, minus the sum of Ij. I guess let's do it. Vi Vj, A bar Ij. And this is sum of Vi square minus sum of Vi Vj, Gij square root Di square root Dj. And Gij is 1 when the edge is 1. So what we got is that sum of Vi squared minus Ij is an edge. I guess but Ij and Ji are both edges, so that's why you get a 2 here. 2 times Vi over square root Di times Vj over square root Dj. And now you can break this first thing I, and then you take J, Vi. Okay, I guess maybe let's try this way. So I'm claiming that this is equals to sum of Vi over square root Di minus Vj over square root Dj square, and Ij is in E. And why this is true? This is true. You can expand this inequality, this equation into terms, and you can see the cross term match this one. The only thing is to see the other terms match the Vi's, right? So we can verify that by looking at sum of Ij in E, Vi square over Di. As this is sum over I, sum of J, such that Ij in E number. Okay, I think this is probably obvious, but I'm making it a little bit too complicated. So Vi square over Di times this way. If you sum over I first and sum over J second, or you first sum over J and then sum over I. So how many edges are connected to I? That's basically Di. So you get this Vi square over Di times Di. So that's why sum of Vi square. Okay, so okay, sounds good. So the point here is that I guess I'm somehow missing a constant somewhere. I'm not sure what. Did I miss a constant somewhere? I will double check. I think the constant might be off by 2 somewhere, but you get the gist, right? Okay, so and if this is regular graph, if G is regular graph, say kappa regular, Then you can ignore the i's. You can just say V transpose LV is 1 over kappa times ij in E Vi minus Vj squared. Okay. So, but why I care about it, why I did so much work to kind of get this equation? I think the equation is very important because this is how it links to how this algebraic quantities links to the conductance, right? So this is still a larger algebraic quantity. It's something like linear algebraic, right? It's a quadratic form. However, if you here suppose now you restrict V to be binary. So suppose V is, you take V to be binary, is a binary vector. And you take S to be the support of V, right? So the indices where the entry, the V is 1, then you can see that from this formula, V transpose LV is 1 over kappa times E Vi minus Vj squared. And when this is 1 when I and j are in both in different. So this is only 1 if I in S and j is in S bar, or I is in S bar, j is in S. Right. So basically, you know, this sum is the number of edges between S and S bar, because only when the I and j is an edge across the groups, this Vm minus Vj squared is equal to 1. Otherwise, it's equal to 0. So this is why it's 1 over kappa times the number of edges across n S bar. So the quadratic form connects to the number of edges across the two groups. When V is not binary. If V is not binary, of course, it's not true. But if it is binary, it's true. So, and now, or in other words, you can write V transpose LV is 1 over kappa, the support of V, the support. So, and now suppose if the support of V, the size is less than 1 over 2, so you have the volume is less than, so this means that the volume of this S is less than the volume of V over 2. Because this is a regular graph, the volume is really just the size of the set. And then in this case, V transpose LV over this ratio, V transpose LV over the norm of V squared, this becomes 1 over kappa times the number of edges between S and S bar. And what is the volume of, what is the V norm square? This V norm square is really the size, this is just equal to the size of S. The size of S is really just the volume of S over kappa. Right. The volume is the number of edges connected to S, and it's regular graph. That's why the volume is just kappa times the size of S. So then you cancel the kappa, you get E of S bar over the volume of S. So this is the conductance of S. So basically, the conductance of S can be written as this form, and this form is some kind of linear algebraic form. And I think this is V transpose LV over norm of V. This is called Rayleigh quotient. And I think this is the name of this. This is named Rayleigh quotient, and the point here is that this Rayleigh quotient connects to the conductance. But of course, it's not exact because it requires when V is binary. Right. So if you do eigenvectors, you are trying to, so eigenvectors means you are minimizing Rayleigh quotient. Without any constraints, right? Constraints on V, right? But the minimal conductance, the sparsest cut, basically means minimize Rayleigh quotient with the binary constraint. And in some sense, this Cheeger inequality, the core is really that even without a constraint, with the constraint, without a constraint, you don't really differ by that much. So actually, the proof works like something like you first try to find eigenvectors, and then you get some real number of these. The eigenvectors have real numbers, right, in V, and then you round it into binary vectors, and then you say by rounding it, you don't lose too much of the related quotient, and that's how the proof, roughly speaking, works. So I guess that's the main intuition. And all of this, can be extended to weighted graph. Like the intuition is the same for weighted graph, or for for graphs that are not similar, not regular, and also for graphs that are weighted. Right. So here the graphs are just binary, like 0 or 1. There's no any other ways. You can also do it for weighted graph. Any questions so far? Okay, so great. So I hope that I've convinced you that the eigenvectors are very related to the graph clustering by these two examples, stochastic block model and this worst case situation. And this kind of like algorithm has been used. So if you do this spectral clustering, this is you can actually use this like okay, how do I say this? So the materials I presented, this mostly come from the theoretical computer science community, and there it doesn't have much to do with machine learning, right? So what the people care about is that you just want to partition a graph into two clusters, so you don't have to know machine learning to define a problem to study this. And I think like there's a so-called spectral clustering approach. Spectral clustering. This was brought to machine learning community, I think around 2000. I think I guess I said this paper by Shi and Malik, and in Jordan was this 1000. And the way that you do it is that you define a graph from the machine learning data, and then you apply this algorithm. So basically, this brings us to the question of how to choose this graph. So how to choose or design the graph? Because the graph, in TCS, the graph is given to you. Maybe some graph that somebody gave you. But in machine learning, you have to somehow choose your graph, right? So in the Andrew's paper, the definition of the graph is something like this. So you first say you give it some raw data, say x1 up to xn. So these are untraining data points. And then you define a graph G to be something like Gij. This is a weighted graph. I didn't really discuss the weighted graph, but there's a natural extension to weighted graph. And then the weighted graph, the weights between I and j is something like exponential minus xi minus xj to norm over 2 sigma squared. I guess this is probably something that is very familiar to you. This is just the RBF kernel, the Gaussian kernel. So define this with some training parameters, or you can have some other variants, right? So I guess you define a graph based on some distances between the raw examples. And then what you do is you say you get a spectral class, you get the eigenvectors. So the first step you define a graph G, and you get eigenvectors of the Laplacian and the normalized adjacency matrix. And here, it's not only two clusters. You can do multiple clusters, and when you do multiple clusters, what you do is you say you get eigenvectors, say U1, U2 up to UK. Suppose you want to have K cluster, and this is a matrix of dimension R of n by K, right? So each column is an eigenvector, and you have k of these eigenvectors. And now what you do is you say you take the rows as the embeddings. Or in the modern world, you call it representation, because probably some of you heard of representation learning. So, and for the ith example, so basically you can map. So for every example, xi, now it becomes represented as maybe let's call this row vi, which is in dimension k, and it corresponds to how many eigenvectors you take. And then you get these low dimensional representations, maybe k is something like 2 or 3. And then in the original paper of Andrew's paper, I think you do some kind of another k-mean clustering, some other clusterings. Say k-means. I guess probably heard of k-means. K-means on the representations. And to cluster them again. So this is the so-called spectral clustering algorithm, and there were actually later, I think around 2014, 2013, there were a few papers that analyzed this, and show that you can actually get reasonable representations and clusters by using this approach. Any questions? So what's the issue with this? The issue with this is that the graph G could be not very meaningful. So in high dimension, so all the data points are very far away from each other. All the training data points, I should be precise. Far away from each other. So this and the Euclidean distance becomes, like Euclidean distance between these training data points becomes pretty much meaningless, because if you take a Euclidean distance of a cat and dog versus the Euclidean difference between dog and dog, you probably wouldn't see much differences, because two dogs could still have very big Euclidean distance. Two random dogs. So, and I think this is in some sense the problem with this kind of approach. The graph itself is not meaningful. So even you find the sparsest cut for the graph, if the graph itself is not very useful, even finding the sparsest cut is not that important. It's not that useful for you. So that's why the theory and analysis for this spectral clustering algorithm, doesn't really kind of deliver that much, because it didn't really consider how the graph was generated. Right, all of this theory says that if you're given a good graph, you can find the sparsest cut for this graph using this approach, but it doesn't really say anything about how the graph is generated. So I think for the last 15 minutes, I'm going to discuss briefly discuss one of this is one of the work in my group recently. So where we try to reuse this classical idea, but use it for in a different way. So this is in one of this paper by Houghton et al. In my group. So what we are trying to do is that we say you consider infinite graph. So GVW, so this is the vertices, this is the weights on the edge, and where we take V to be all the possible inputs. So this is the all possible data points. So this graph is defined on the population space, right? So X is the basically space of all possible, say, images and your graph is defined on each image corresponds to a vertex. So before the graph has size little n, where this is E. So before the graph has size little n, right? It's a little n by little n matrix, and now the graph has much bigger size. The size is the same as the cardinality of all possible data points, which could be infinity. So so for simplicity, maybe let's say you have finite number of possible images, but n could be exponential. So for simplicity, let's say we have exponential size graph. So then so on this graph, what you do is you define wx prime, the weights between two nodes, two vertices. Let's say define this to be large only when x and x prime are close in L2 distance. So I'm still using L2 distance. I'm still probably using, I'm not specifying exactly what's the definition here because I think that requires too much jargon, which I can offer in 10 minutes. But still, we are using pretty much, you can think of this as almost the same as the previous definition of the graph. When x and x2 prime are close, but I guess the point is that this is very close. So before, you have to choose the sigma very subtly because all the points are very far away from each other, right? So, but now you say that I don't care about those points that are far away from each other. I just care about those 2 points that are very close to each other, right? So suppose you have 2 dogs, random dogs, you say they are not close. If you only have 1 dog and you have a perturbation of that same dog, you say there are dogs that are connected to each other. So then this graph becomes more meaningful because you only connect very nearby kind of cats and dogs, very nearby images. And then the graph becomes more meaningful. So the pros is that the graph is more meaningful. I guess the cons is that it becomes infinite dimensional. And you don't have this graph because you don't know all the possible data points. You only have some sample data points. So or infinite or exponential dimension. And you don't have access to this graph. So what we do is the following. So the way we fix the cons is the following. So, and also maybe another way cons is that even the eigenvector itself, right? The eigenvector is also high dimensional, right? It's infinite dimensional. Because the eigenvector, the dimension of the eigenvector is the same as the dimension of the graph. So, however, here what we are doing is that we use the new ideas, the deep learning ideas, to kind of actually the real research is the reverse direction. We somehow try to explain the deep learning ideas, but here in this context, you can think of this as you use the parametric neural network kind of ideas to try to deal with these cons. So what you do is you say, suppose you have an eigenvector u. This is the eigenvector. So this is the eigenvector u, and here the eigenvector is a high dimensional vector, so you can say this is ux, where it's indexed by all the possible data points in the capital X. Right, this is of dimension something like maybe r to the capital N or r to the infinity, depending on how many vertices in your set. So, and you don't even have space to save all of this. Even a single eigenvector, you don't have even space to save it. But what you do is you say you represent this u sub x by a neural network applied on the raw data point x. So where f theta is a parametric model. So if you do this, then at least you can describe the eigenvector by theta. Now, you don't have to specify all the capital N numbers to specify the eigenvector. You only have to specify the theta to describe this eigenvector. Of course, there's a, if you believe that f theta is powerful enough, then you can express any vectors. But of course, f theta probably wouldn't be enough, so you have to make some assumption that neural networks can represent these kind of eigenvectors. But suppose under that assumption, then you can at least represent the eigenvectors by theta. And now, basically, the question becomes like, so the question changes to, you want to find theta such that this vector f theta x, right, this very high dimensional vector, is an eigenvector of the graph G. So at least you are trying to find a low dimensional you are trying to find a parameter theta, right? You are not trying to find a high dimensional vector anymore. And it turns out that if you do this, I guess maybe eigenvector Laplacian. Let's see. I think I have time to. It turns out that if you do this, then this is basically trying to do this gives a. You can design algorithm that try to achieve this. I guess I'm trying to, let me see whether I have time to. I guess what we can do is the following. So what you do is you say, I'm going to, how do I find an eigenvector of L like this? So suppose I have the access to the whole graph, which I don't, but suppose I have it, what I can do is I can minimize the following thing. So I can say I'm going to minimize f. Let me write it down. So maybe let's do this just for simplicity. A bar f is an n by d matrix. So first of all, I claim that this gives the top eigenvector of A bar. This is because this is something that I probably wouldn't have time to explain that much, but if you want to fit a low rank matrix, this is n by k, the top k eigenvector. So if you want to fit a low rank matrix to the matrix A bar, the best fit would be to use the eigenvectors of A bar. So this is there you can invoke a theorem to show this. So basically f is going to be some version of the minimizer of this will be some version of the eigenvector. So I think f will be the minimizer of this will be some scaling of the eigenvectors. And then if you use this objective, then you can replace the capital F, which is non-parametric, it's a very big matrix, by, so you can say that the capital F now for now is supposed to be something like this, right? So, and then you write it as this. You write it as f theta x transpose x1 up to f theta x then transpose. So you replace the row by the parametric version. So you say that every row now is a neural network of the raw data. And then what you can get is that this will be, if you write this as, in this version, this is like, first of all, you write the forbidden norm as a sum over ij in n, a bar ij minus, so ff transpose ij. The ij's entry is the ith row in a product with the jth row. So that's why this is equals to f theta xi times f theta xj square. And I can change this to, instead of minimizing f, now you are minimizing theta. And I guess I don't have time to go through all the details, but you can, this is basically, this is a now objective function that you can optimize. Of course, the problem is that you still have this sum, this big sum. You can replace this by the empirical version. So you can get minimized over theta. You can take some random samples. So you can take, I guess I'm not sure whether I have a way to simply write this. So you can okay, maybe I'll just say you can subsample this. So like estimate this using empirical estimate using empirical examples. And actually, it turns out that if you simplify this formula, this will be something similar to the contrastive learning algorithm that is used in practice. I guess this part I don't really have time to show. I guess I'll refer you to the paper. I think probably I should just stop here. Are there any questions first? But like this, I know this part is a little kind of vague. Feel free to ask any questions.
Do you know the name of the contrastive paper we could look at off the top of your head?
The paper, I think probably it's good to write just a, yeah. I think like the loss is not exactly the contrastive learning loss used in practice. So we're gonna have something we call spectral contrastive learning loss. So basically, actually, this step, if you have all the setup, then this step is pretty trivial. So eventually, if you simplify this a little bit, what you're gonna get is that you get one term which is minus a half f theta xi, f theta xj, and this is something like the term that tries to make two examples closer to each other, and there's another term that tries to contrast them. But there's another, so anyway, so I guess I probably just will refer to the paper of our paper. I think the title of the paper is that something like provable self-supervised learning via spectral contrastive loss, something like this. I think from this you can search the find title. Yeah.
So before the section just before this one, you mentioned looking at they can look at the eigenvectors, line them up, and then take the first row of that matrix and say that corresponds to the first data point, and then what exactly is that correspondence? How come if the first and the second row are similar, then the first two data points should be similar?
I think I got the question. So I think there is something that I kind of I understand why there's a little bit of confusion, because I skipped something about the K, how do you deal with K clusters? But I think this could be seen when you have only, if you take a little bit leap of faith between K clusters and two clusters, you just say this is two cluster. And then if you look at let's see, so where did we discuss this? I think we discussed this somewhat implicitly several times. So I guess, for example, suppose you go back to here, and recall that the second eigenvector looks like beta 1 up to beta n, right? So, and we discussed that you take a threshold, and then you can separate the two groups, right? You threshold. So in this case, basically, suppose you have two clusters, and in this case, basically, the beta I is your representation of the ith vertex. So that's the row, right? That beta 1 is the first row, right? Beta 2 is the second row, right? So beta I is the representation of the ith vertex. And why beta I is better than the raw data? I think this is because, at least if you threshold beta I, you get the groups, right? So basically, in some sense, beta I, in some sense, maybe the ideal thing is that following. So you suppose you, in the stochastic block model, get this. And then I guess you probably can agree that these numbers are better representations than the original data, because now you map all the vertices in the same group to 1. right? So just you lost all the other information. You just get the representation just exactly tells you about the group membership, and you don't know anything about else, right? So the group membership is the only thing you care about. So that's why these numbers are more like better representations than the.
This is kind of similar to the like low rank matrix approximation, approximated by low rank matrix, and you know, that's just a better representation because we've kind of taken the most important parts of the representation.
Exactly, and what's the most important one? The most important one here, in this case, the most important one is the clustering structure, right? So which group you belong to, right? So that's why the only thing you care, suppose if you think that's the most important information, then your representation should just be that you ignore any other information. You just say the group ID is my representation, and that's the best representation.
Well, that's only because in this case we said there's 2 clusters.
Right. Right.
Then we care about the 2 cluster kind of representation, but we also care about maybe like a 3 cluster representation and like how close things are based on that. And so by taking multiple eigenvectors, we can kind of get a bigger picture than just like in this cluster or not.
Exactly. So if you have more eigenvectors, then you can get 3 cluster information or even more information. And also this can be, some of this information can be recombined to get even richer information, right? So because eventually you probably use this representation by a linear plus use a linear head on top of it. So suppose you have 2 types of information in your system, then you can actually combine them to get more information. Yes, but you are right. So basically, if you get more eigenvectors, you get more richer information from the graph. Yeah, so essentially it's kind of like matrix factorization. You distill the information in the graph to smaller amount of information. And the kind of the question we are trying to answer is that what information you keep in the eigenvectors, right? So it's not that surprising that the eigenvectors has like a more succinct information about the graph. The question is what kind of information it keeps, and the kind of the rough intuition is that it does keeps the clustering structure in the graph, but not other things, right? Like at least the smallest eigenvectors are trying to keep the clustering structure of the graph. Okay, great. I think this will be the end of the quarter. I guess I hope you liked the course. I guess we discussed quite a bunch of topics. And this quarter, I think we covered the most compared to all the previous quarters partly because we have we have 10 minutes every class and every lecture, and also we have 2 more lectures because we have fewer holidays in this quarter. Yeah, I guess I hope you like it. Thanks so much for attending.